right, hello everybody. I'm Robin Velasquez,
Mandy Stutz.
Jasmine Williams.
Seth Norris.
and we are the detection and analysis of electromagnetic interference and electrostatic discharge, which was only made possible through our lovely sponsors that you can see there.
We were provided a device from Peterbilt, which we were tasked with analyzing the ESD and EMI components, the AC and DC components, and their associated risks. Our biggest constraints were time, quality, and safety.
So as you can see here, this is our setup. Our DC power supply would supply power to our device under test, which was housed inside an RF anechoic chamber, along with our log periodic antenna. And then it would send a feedback of a sinusoidal wave to make sure that it was working correctly. It would also produce a negative 100 kilovolts charge at its tip, and the EM field was being read by our analog antenna and then sent out to our device that we use to measure the frequencies and strengths with.
In order to determine our costed losses, we had to do preliminary testing. We determined the air loss, the path loss, the cable loss, the antenna gain, and the attenuation loss, as well as determine the viability of our equipment.
We tested 2 different devices, and we found a consistent 30.6 megahertz signal across both outputs.
When we looked at the AC signal in the time domain, we were able to see an anomalous AC signal that wasn't originally supposed to be there. We suspected it was coming from the power supply, but we were able to determine that it was actually emanating from the device itself.
As you can see, we calculated power received, and then we calculated from there the power transmitted from the device itself, which we then later used to calculate the electromagnetic field strength given the known constants that are below there to be 12.39 volts per meter.
Yes.
We used FCC regulations as our engineering standards. The human exposure limits were well within range. The interference conducted limits, we exceeded greatly, with our electric field being 12.4 volts per meter and the limit being 90 microvolts per meter.
For DC analysis, we determined there was 2.5 kilovolts at 25 inches. Using the system level ESD model, a discharge would have 9.375 amps, which well exceeds the safety ratings of microelectronics.
These are some of our resources that we use to check our work, and
Thank you.
Thank you.
Thank you.
Are there any questions? Sorry.
Can you say anything about the devices under test? What type of components were they, or systems? Or?
Due to an NDA, we cannot disclose the nature of the device besides that it was it had a DC power supply and that it produced a negative 100 kilovolt DC as its tip.
It was a system, though. It wasn't an individual component.
Yes.
Yes.
So basically, you tested a component, you saw some leakage, and the leakage was within safe limits for humans, right?
Yes.
Okay, but what about interfering with other devices?
It does. It exceeds microelectronics ratings, which was the main concern of this project. So that's why we tested the FCC regulation, and as you saw, it was only 100 microvolts, and we were 12.4 volts as our potential.
Okay, so you're way above.
Yes.
Yes.
So somebody's got to do some shielding or some additional.
Right.
Was your anechoic chamber certified? Did you know its characteristics?
We did.
Yes.
Yes.
You
We
want a copy, Ed?
received it from ETS Lindgren. And let's see, the limits.
Was it 30 to like 2 or 30 to 4?
I think
We
so.
believe it was 30 megahertz to 4 gigahertz rated. And since our 26 megahertz to 4 gigahertz. And since our signal was 30 megahertz, it was viable for our system level. So it should have shielded from both interference in those ranges as well as for any reflections that could happen.
Do you know if the device that eventually went off through that final certification between the certification body?
We do
not know.
Any other questions? Thank you very much for your time.
Thank you.